Here we're asked what happens to the capacity of a channel as the bandwidth is increased indefinitely. So as we increase the bandwidth towards infinity, does the channel capacity also increase indefinitely? So we'll start with the Shannon-Hartley theorem, or the Shannon-Hartley law, that quantifies the relationship between channel capacity and bandwidth. So you'll see that channel capacity is directly proportional to bandwidth if the signal-to-noise ratio is constant. So we're being asked to find the limit as the bandwidth approaches infinity. What happens to the channel capacity? So at first sight, it looks like as this approaches infinity, so does this. But is that the case? Is it true that the signal-to-noise ratio is independent of bandwidth? Now we know that the noise power increases as the bandwidth increases. So we know that the more bandwidth we have, the more noise we have. And the constant of proportionality is called the noise spectral density, or the power spectral density of the noise, N0. So that is a constant. So the noise power is directly proportional to B. So now we have B twice in this expression. We have the bandwidth here, but we also have the bandwidth here. So it's now no longer that simple. So as B approaches infinity, this will increase, but so will this. And how will that affect our calculation? Now we're allowed to use this hint that we're given in the question that, let me just put a little one there. So the limit as x approaches 0 of 1 plus x to the power 1 over x is e. So if we somehow rewrite this so that we have 1 plus x to the power 1 over x, then we can use this approximation. So we need somehow to get the reciprocal of this up there, or right there, multiplied by the log. So if we invert that, we can now introduce these, which conveniently cancel out. So it's as if we've made no change to the expression, but what that allows us to do is to have the reciprocal of this here, so that if this was x, this would be 1 over x. And because it's a logarithm, I'm allowed to bring that up and turn it into a power. So that's my 1 over x, and that's x. So that is my 1 over x if that were x. And I can now say that all of this approaches e. So I can say that all of this approaches e. So I can replace this expression with log 2 of e. So that is there. So now we end up with this expression here, where the channel capacity isn't increasing indefinitely, it's approaching some constant, because this is a constant. This is a constant, the noise power spectral density. This is how much power there is in every watt, how much noise power there is in every hertz of bandwidth. And this is the signal power. That's constant, that's constant, that's constant. So it looks like the channel capacity isn't increasing indefinitely, it's approaching some constant. So 1.44, that's log 2 of E. So if we were to plot a sketch of B or C against B, rather than having it increase indefinitely, we have it approaching 1.44 S over N naught. So this is the upper bound for channel capacity. So channel capacity has an upper limit, and that upper limit can be found. It requires a little bit of mathematical approximation and manipulation, but that's how you would find the channel capacity as the channel bandwidth is increased indefinitely.